Hello dear students, this is our third recorded lecture for Probability Theory course. Today we will talk about probability. We assign a probability measure P of A to an event A. This is a value between 0 and 1 that shows how likely the event is. If probability of A is close to 0, it is very unlikely that the event A occurs. On the other hand, if probability of A is close to 1, A is very likely to occur. The main subject of probability theory is to develop tools and techniques to calculate probabilities of different events. Probability theory is based on some axioms that act as the foundation for the theory. So let us state and explain these axioms. The first axiom is for any event A, probability of A is greater than or equal 0. Axiom 2, probability of the sample space S is equal to 1. Axiom 3, if A1, A2, A3 and so on are disjoint events, then probability of A1 union A2 union A3 equal probability of A1 plus probability of A2 plus probability of A3. Let us take a few moments and make sure we understand each axiom thoroughly. The first axiom states that probability cannot be negative. The smallest value for probability of A is 0, and if probability of A equals 0, then the event A will never happen. The second axiom states that the probability of the whole sample space is equal to 1. The reason for this is that the sample space S contains all possible outcomes of our random experiment. Thus, the outcome of each trial always belongs to sample space. The third axiom is probably the most interesting one. The basic idea is that if some events are disjoint, then the probability of their union must be summations of their probabilities. Another way to think about this is to imagine the probability of a set as the area of that set in Venn diagram if several sets are disjoint, such as the ones shown in the past figures. Then the total area of their union is the sum of individual areas. The following example illustrates the idea behind the third axiom. If a welfare die, we roll it. The outcomes are 1, 2, 3, 4, 5 and 6. These events or these outcomes are disjoint. The probability of the unions are equal to 1. The equally likely outcomes, probability of A is equal the number of events or the number of occurs that the event A occur divided by the number of events or the number of outcomes or the number of objects in sample space. Suppose that we are given a random experiment with a sample space S. To find the probability of an event, there are usually two steps. The first step is we use the specific information that we have about the random experiment. Second, we use the probability axioms. Let's look at an example, although this is a simple example and you might be tempted to write the answer without following the steps. We encourage you to follow the steps. If you roll a fair die, what is the probability of event 1 and 5? Let's first use the specific information that we have about a random experiment. The problem states that a die is fair, which means that all 6 possible outcomes are equally likely. Means that probability of 1 equal probability of 2 equal probability of 3 equal probability of 4 equal probability of 5 equal probability of 6, and probability of sample space equal 1. So the probability of event 1 and 5 equals the probability of 1 plus probability of 5, which is 1 over 6 plus 1 over 6 equal 2 over 6. Using the axioms of probability, prove the following. 1. Probability of A. What is the probability of A complement? This states that the probability that A doesn't occur is 1 minus probability of A. To prove it using the axioms, we can write probability of sample space equal 1, probability of A union A complement equal probability of A plus probability of A complement. Thus, probability of A complement equal 1 minus probability of A. The second, since phi equal sample space complement, we can use part A or part 1 to see that probability of phi equal 1 minus probability of sample space equal 0. Note that this makes sense, as by definition an event happens if the outcome of the random experiment belongs to the event. Since the empty set doesn't have any element, the outcome of the experiment never belongs to the empty set. Number 3, from part A, probability of A equal 1 minus probability of A complement, and since probability of A complement is greater than or equal 0, we have probability of A less than or equal 1. Number 4, prove that probability of A difference B equal probability of A minus probability of A intersection B. We show that probability of A equal probability of A intersection B plus probability of A difference B. Note that the two sets A intersection B and A difference B are disjoint, and their union is the set A. Thus, by the third axiom of probability, probability of A equal probability of A intersection B union A difference B. Since A equal A intersection B union A difference B, which is equal probability of A intersection B plus probability of A difference B. Note that since A difference B equal A intersection B complement, we have shown probability of A equal probability of A intersection B plus probability of A intersection B complement. Note also that the two sets B and B complement form a partition of the sample space. This is a simple form of law of total probability that we will discuss shortly, and is a very useful rule in finding probability of some events. Number 5, note that A and B difference A are disjoint sets and their union is A union B. Thus, probability of A union B equal probability of A union B difference A equal probability of A plus probability of B difference A equal probability of A plus probability of B difference probability of A intersection B. Finally, number 6, note that A is a subset of B means that whenever A occurs, B occurs too. Thus, we expect that probability of A is less than or equal probability of B. Again, the proof is similar as before. If A is subset of B, then A intersection B will be equal A. You have to solve this exercise. Rolling a die twice and observed x1 and x2. Find the sample space. Find event A. If x1 plus x2 equal 4, find the elements in A and the probability of A. Number C, if event B is x1 plus x2 equal 6 or 7, find the probability of B. The summary: A is subset of the sample space, so the probability of A is greater than or equal 0. Probability of sample space equal 1. A1, A2, and so on are disjoint sets, and the probability of A1 union A2 union so on equal probability of A plus probability of A1 plus probability of A2 plus so on. The finite sample space with equally likely outcomes is equal to probability of A equal A divided by S. There are two types of the sample space. The first type is the countable for discrete probability space, which is such as A equal A1, A2, A3, and so on, and the probability of A equal probability of A1 plus probability of A2 plus probability of A3, and so on. The second type of the sample space is the uncountable for continuous probability space. The following topic is the conditional probability. In this section, we discuss one of the most fundamental concepts in probability theory. Here is the question: as you obtain additional information, how should you update probabilities of events? For example, suppose that in a certain city 23% of the days are rainy. Thus, if you pick a random day, the probability that it rains that day is 23%. Now, suppose that I pick a random day, but I also tell you that it is cloudy on the chosen day. Now that you have this extra piece of information, how do you update the chance that it rains on that day? In other words, what is the probability that it rains given that it is cloudy? If C is the event that it is cloudy, then we write this as probability of rainy given that cloudy. The conditional probability of R given that C has occurred. It is reasonable to assume that in this example, probability of R given C should be larger than the original probability of R, which is called the prior probability of R. But what exactly should probability of R given C be? Before providing a general formula, let's look at the following definition. The conditional probability A given B. The probability that A occurred given that B has occurred is given by probability of A given B equal probability of A intersection B divided by probability of B when probability of B is greater than 0. If you roll a fair die, let A be the event that the outcome is an odd numbers. A equal 1, 3, 5. Also, let B be the event that the outcome is less than or equal to 3. What is the probability of A? And what is the probability of A given B? Now, let's find the conditional probability of A given that B occurred. If we know B has occurred, the outcome must be among 1 to 3. For A to also happen, the outcome must be in A intersection B, which is 1 and 3. Since all die rolls are equal likely, we argue that probability of A given B must be equal to probability of A given B equal probability of A intersection B divided by probability of B, which is 2 over 3. Now let's see how we can generalize the above example. We can rewrite the calculation by dividing the numerator and denominator by sample space is the following way. Although the above calculation has been done for a finite sample space with equally likely outcomes, it turns out the resulting formula is quite general and can be applied in any setting. It is important to note that conditional probability itself is probability measure, so it satisfies probability axioms. Axiom number 1: for any event A, probability of A given B greater than or equal 0. Axiom 2: conditional probability of B given B is equal to 1. Axiom 3: if A1, A2, A3 are disjoint events, then probability of A1 union A2 union A3 given B equal probability of A1 given B plus probability of A2 given B plus probability of A3 given B. Let's look at some special cases of conditional probabilities. The first special case is when A and B are disjoint. In this case, A intersection B equal phi, and the probability of A intersection B equal 0. So the probability of A given B equal probability of A intersection B divided by probability of B, which is equal probability of phi divided by probability of B, and we said that probability of phi equals 0, so probability of A given B equals 0. This makes sense. In particular, since A and B are disjoint, they can't both occur at the same time. Thus, given that B has occurred, the probability of A must be 0. The second special case, when B is a subset of A, If B is a subset of A, then whenever B happens, A also happens. Thus, given that B occurred, we expect that the probability of A be 1. In this case, A intersection B equal B. So, probability of A given B equal probability of A intersection B divided by probability of B, which is equal probability of B divided by probability of B. It is equal 1. The third special case of the conditional probability, when A is a subset of B. In this case, A intersection B equal A, so probability of A given B equal probability of A intersection B divided by probability of B equal 1. If we roll a die, what is the probability that it is larger than or equal to 5, given that it is an even number? Suppose that in a certain city, 0.3% of the days are rainy. Probability of rain equal 0.3. The probability that it rains given that it is cloudy might be probability of rain given that cloudy equal 0.9. The formula of the conditional probability is probability of A given B. If we have two events A and B are independent, if and only if probability of A given B equal probability of A, probability of A intersection B equal probability of A times the probability of B, so that probability of A given B times the probability of B equal probability of A times the probability of B, and the probability of A intersection B equal probability of A times the probability of B. We have to distinguish between disjoint and independent. Disjoint or mutually exclusive doesn't equal independent events. Disjoint means that A intersection B equal phi and the probability of A union B equal probability of A plus probability of B, and the independent sets are when probability of A intersection B equal probability of A times the probability of B, which is indicate for probability of A given B equal probability of A, and the probability of B given A equal the probability of B. Suppose A and B are disjoint. If probability of B not equal to 0, so the probability of A given B will be equal probability of A intersection B divided by probability of B, which is probability of A intersection B, which is equal to 0, so the probability of A given B will be equal 0. If probability of A not equal to 0 and probability of B not equal to 0, they are disjoint and not independent. Remark the following points. The first point, probability of A given B equal probability of A, and probability of B given A equal probability of B for independent sets or independent events. If A and B are independent, then A complement and B complement are independent. A and B complement are independent. A complement and B are independent. Thank you.